So the first thing we're going to do is we're going to solve this thing. And then what I'm going to do today is I'm going to talk about diodes. So we'll do a thing on diodes. All right, so to start off with this problem, what makes it a bit different this time is we've got inductance and capacitance. So they refer to this as an RLC circuit. This one is in series. So the circuits I've done are all in series. A lot of the stuff you're going to be seeing coming up in the motor course, you're going to be seeing stuff in parallel. When you're dealing in parallel, the easiest thing to do is to find currents, and then you solve with the currents. This one is very easy because it's in series. The way we add up our stuff in series is very simple. It's different when you do circuits in parallel. Because doing stuff in parallel, well, you've got to, you remember how you used to do resistance in parallel? You'd say 1 over total resistance is equal to 1 over this. So you've got to do the same kind of thing with this. It means you've got to add and subtract. You've got to add more or less. And that means you're going to have to turn what we have polar values here, you have to turn them into rectangular. So it's a bit of a pain in the butt if you try to do it the same way. When you're doing parallel stuff, you're best using currents. But you'll see that in the motor course. Anyway, we'll start off with this thing. So the first thing you should solve for is XC and XL. So if I do XC, I'm going to say 1 over 2 pi. The frequency is going to be 60 hertz. And our capacitance here is 27 microfarads. So what did you come up with?
98.24.
98.24
at an angle of -90.
That's right, it's at negative 90 degrees. For XL, well, it's going to be 2 pi times, again, the frequency. But this time it's going to be inductance, so 330 millihenries. So what did you get for that?
124.4 ohms at an angle of +90.
Okay, so here's what we get. This is our XC, this is our XL. So if we just do, for now, if we just do a little vector diagram of our reactances and resistance for this circuit, what we're going to find is the following. So we're going to have one vector for XL pointing upwards at 90 degrees. We're going to have another similar vector, a little less, which is going to be XC pointing downwards. And we're going to have, of course, our resistance over here. So those are our reactances and our resistance right now. So one of the easiest things to do at this point is let's just take care of XL and XC. We'll call the resultant, we'll call it X1. All right? Because they're in the same plane, okay? They're just one against the other. So the easiest thing to do is to say, well, X1 is going to be, well, which one's the biggest one? Biggest one is XL. So we're going to go XL minus XC. So we'll take 124.4, take away 98.24, and that's going to give us, you get if you do that.
26.
How much?
26.
36?
26.
26.
0.1.
This is ohms. And that 26, is actually pointing, I'm doing in green. It's the difference between these two. That's X1 right there. So that means our impedance is going to be the sum of R and X1. So our impedance, this vector right here, Z total, is actually going to be the sum, the vectorial sum of X1 and R. All right? So if we work that out, Z total, I'm going to do the same thing. I'm going to go, okay, that's the square root of X1 squared plus R squared. So I'm going to square root. That's X1 is 26.16 squared plus 100 ohms squared, and take the root of that, and I think I get something like 103?
Yeah.
0.4.
103.4. Okay, so 103.4 ohms. Now we'll find the angle. So the angle here would be, all right, so the inverse tan of x1 over r. So we're going to go 26.16 ohms over 10 over 100. So you do 14 degrees?
0.7.
Okay, 14, we'll go 14.7 degrees. So this thing over here is at 14.7 degrees positive. We know that because we drew our vector. These diagrams are really helpful when you're doing the math because you can predict, where the angles are going to be. You get a good visual. You know that x1 had to be plus 90 because xl was bigger than xc. So you know that zt is going to have a positive angle just by the diagram. And because r is much bigger than x1, yeah, we'd have a small angle. Makes a lot of sense. Everybody's with me so far? Okay, so I'm going to go straight to calculating the real power and the apparent power, and I'll get the power factor right away. So here's what I do. I look at the real power, and I know that the current going through the circuit, so we're going to go find the current. I know it's going to be I total. So we'll use the total impedance. We'll find the current right away. So I'll go IT is going to be the total voltage at 0 degrees over the total impedance. So in our total impedance, we know that the total impedance is at 14.7 degrees. So we go, okay. So our total voltage for our circuit is 10 volts at 0 degrees. And our total impedance, we just figured it out, is 103.4 at 14.7 degrees. So we got a pretty good idea. It's probably be milliamps, probably. That's what I'm thinking. So I know the angle. If I look at the angle, it's going to be 0, take away 14. So we know the angle is, for our current, is lagging. It's at negative 14.7. If I do 10 volts and I divide it by 103.4, what do I get?
96.7 million.
So 96.7 milliamps. Holy crap, you guys did your homework. Good job, man. Oh, by the way, our first test is going to be on October the 4th in here. So that should be a Thursday. October the 4th. And it's going to have a problem, one problem similar to this. And the others are going to be multiple choice diode questions. Okay? And just to help you out, if you want to study for your multiple choice diode questions, go online and just type in Google multiple choice diode questions. Go study those. Because I'm a very lazy guy, and what I do when I make my tests, I go and rip off, copy and paste off all these little tests that I find, and I use those for test questions. So if you're studying online, there's a good chance you're going to run into the questions that are going to be on the test. Makes studying pretty cool. Okay, yeah, sweet. And the test will be open book, eh? It's always open book. Yeah.
You just answered my question.
Well, I know. Psychic abilities. Okay, where they pay me to make money. All right, so we've got the current. So here's what we're going to do. We're going to do power real. Power real. Well, we know that the current. I'm going to use for power. I'm going to use this formula. I'm going to say power I know is equal to I squared R. So I don't even need voltages. Okay, we know power is equal to I squared R. So I'm going to take I total. I'm going to square it times the real power is dissipated on the resistance. So let's go take a look at the power on the resistance then. So we're going to go, all right, times R. So I'm going to take a current of 96.7 milliamps at negative 14.7 degrees times squared, so times 96.7 milliamps at an angle of negative 14.7 degrees. And then I'm going to go times 100 ohms at 0 degrees. That works out pretty well. So the angles, you add them up. So negative 14 plus negative 14. So this should be like 29.4. So the angle is going to be negative 29.4 for all that matters. So you take 96.7 milliamps times 96.7 milliamps times 100 ohms. You're going to come up with milliwatts. Make sense?
Is it okay if we did IP times VR?
Of course, they're all formulas for voltage.
Okay, so it's 935.09 milliwatt.
Yeah, there's two other formulas for power. So if you went and found the voltages,
Yeah.
works. It's gonna give you the same answer.
Okay.
Okay?
Yeah.
Okay. Power apparent. So power apparent. Here's what I'm gonna do. Same idea. I'm gonna take IT. And apparent power is the power in VAs for the whole circuit. So I'm gonna go times the whole circuit, which is NT. We box this answer for power. This is the power answer for power. Okay. So this one over here, I'm going to do the same business here. 96.7 milliamps. Okay, this is going to be again negative 14.7 times 96.7 milliamps. 14.7, and then times Z total, which is 103.4 at an angle of 14.7. So I got a negative 14, a negative 14, and a plus 14. So the angle, the resulting angle, I know for sure is going to be plus 14.7, and no, negative 14.7. Excuse me. So one negative cancels out a positive, one negative here, and you multiply those together, and this time you're going to get milli VAs because it's apparent power.
Does it matter what formula you use?
No, no, it doesn't matter what formula you use. You're going to get the same answers.
Because we did not get the same answer.
Oh well.
That's why I'm asking. Because we use power real squared plus your reactive power, and then you do the square root of those.
This should work. So there might be a mistake somewhere, but this is definitely going to work. So what do you get milli VAs if you work this out?
967.
How much?
967.
Yeah, 967 milli VAs. All right. So that's your apparent power. All right? Make sense?
Yeah.
Okay. Now, you know where you might have made your mistakes? Probably when you're calculating reactive power. Because if you calculate reactive on this one and reactive on this one, you got to subtract one from the other. That's exactly where you went wrong. See, psychic abilities. Because what happens is one is actually the power on one is 180 degrees the opposite of the other. Okay, one is doing reactive power storing at one time, and 180 degrees later the other one's storing. So you've got to take those reactive powers one from the other, and you've got to use the power that X1 would end up with. Okay? No, God had nothing to do with this. This is all my doing right now. Well, I shouldn't take all the credit. So power factor. So power factor is going to be the following. Okay, so if you want your power factor, you say, let me erase some stuff here. So I'm going to take this off. So your power factor is your real power over your apparent power. So you're going to take your real power, which is 935 in milliwatts, and you divide that by your apparent power, this is 967 in milli VAs, and you come up with a ratio, which is going to be...
Do you still need the angles for this one?
No.
Okay.
These are power factors strictly a ratio. 0.96. 0.96, which is looking good, man, because it's getting really close to 1. So your power factor is much improved. Now let's talk about what that means. Well, if we were in a, in a shop, a factory or something like this, chances are, as the electrician in the shop, you're going to have, you're responsible. You got to take care of the electric. A lot of motors, a lot of inductive loads. So in the building you're in, it's probably motors for fans, there's conveyor belt motors, all that. So these motors, okay, have basically the motor has resistance in it, and it has inductance. The part of the motor that's really good is its resistance, because whatever's burnt on the resistance is actually power that's either, well, we're hoping not much heat, but a lot of work. That motor is doing work. That's the real power. We want a lot of that. But we've got this problem of inductance. Some of the power that's going into the motor is being stored and then it's bouncing. So what we do to counter that is when the power comes into the building and we know that there's inductance in there, we put some capacitance in the system. We actually purposely switch in some capacitors on the line to react against the inductance. Because remember, like our little vector diagram, one was pointing one way, we put in, so we've got inductance going that way, so we put in a capacitor that points the opposite way to cancel it out. And as a result, by putting an inductor in our circuit, putting a capacitor in our circuit, you'll notice that this time, compared to the 2 previous problems, our power factors look, ooh, look how nice it got because of that capacitor. And in fact, what you can do is you can calculate what's called the resonant frequency, and you can figure out the exact value of capacitance that's going to null out this inductor. So there's a little formula, I'll give it to you if you're kind of interested. It's called resonant frequency. So F resonant is equal to 1 over 2 pi the square root of LC. So you can actually work this thing out if you know like our frequency is 60 hertz and you know the inductor is, let's say, 330 millihenry, you could like isolate C and find a capacitor that is going to balance it out perfectly. And when it's balanced out perfectly, we say that the circuit is resonant. So what they do in your business is that when they bring in power to place, they may have like where the power's coming in, they'll have this big cabinet, and it's gonna have a computer in there, and it's gonna watch the phase angle of the current coming into the building, and it's gonna switch in. There'll be a capacitor bank in there, and it'll switch in whatever capacitors it needs to balance out the inductive load. And when the inductive load changes in the building, somebody turns off the motor, it'll switch off capacitors. If somebody turns on more inductive loads, they'll switch on more. It does it automatically. So they have these things to make the power factor as close to 1 as possible. And like I said, if you look at a lot of utilities have tables, and they'll tell you, if you can keep your power factor, 0.9 or higher, there'll be no surcharge. We're not going to be too upset with you. But anything, if you keep your power factor goes below 0.9, they're going to tag some more, there's going to be more tagged onto the bill. All right? So that's our problem right there. So that's part 1.